Greetings to all respected viewers. I, Ritik Raha of NSCC, am presenting a talk on causality analysis of emotional states from EEG response. This is the International Conference for Convergence in Engineering 2020 and the paper ID is 198. Let us start with an overview of the topics we will be covering listed here. Moving on to the introduction, which talks about the motivation of the project. The very foundation of this project is whether our emotions are dependent on each other or whether they are interlinked. The scientific way to express that question is by asking whether corresponding emotional states are causal to each other, meaning whether the preceding emotional state helps in determining the succeeding one. We have here the dataset specifications of the two datasets we have used in this work, the SEED4 dataset and the DREAMER dataset, both of which are EEG signals collected from the response of multiple subjects being shown different film clips for emotional cues. The diagrammatic representation for the SEED4 dataset, where 15 subjects are shown 72 film clips over 3 sessions. The emotional cues so obtained are neutral, sad, feared, and happy emotions respectively. The diagrammatic representation for the Dreamer dataset, where 23 subjects are shown 18 film clips over one session. The emotional cues so obtained are calmness, surprise, amusement, fear, excitement, disgust, happiness, anger, sadness, respectively. This is the proposed model for investigating causality from the datasets mentioned. Since we have two different datasets for parity, we select and merge channels from the EEG headset that we require. The resultant signals are then sampled and filtered as has been specified by the corresponding dataset papers. We then investigate the quality of the signal through PSNR and then move on to extracting feature by a number of steps and perform statistical analysis on them. The pre-processing of the datasets are as follows. The 62-channel ESI neuroscan system has been used by the authors of the SEED4 dataset, and we have used the channels FP1 and FP2 and FPZ, which have been merged, sampled at 200 Hz and filtered in 1 to 75 band range. The 14-channel Emotive Epoch wireless EEG headset was used by the authors of the Dreamer dataset, and we have used channels AF3, F3, AF4, and F4, which have been merged, sampled at 128 Hz and filtered between 4 to 30 Hz. The feature extraction procedure on the resultant signals are broken down in the following steps. We have at first peak signal to noise ratio, or a PSNR. In this context, we use PSNR to determine the quality of a given trial with respect to the succeeding one. This gives us a response of how the quality of trials differ. The mapping of the governing equations to the trials of EEG signals is shown here. The SEED4, the given response for the two datasets, where we see the SEED4 session 2 having strong seasonality among trials, whereas Dreamer having definitive low and high points in the response. Next, we have Manhattan distance. In the context of our work, this has been used to determine how dissimilar the two consecutive trials are, and the distance metric is also useful in providing a measure of outliers in the dataset, if any. Moving on, we see that while SEED4 session 2 again has strong seasonality, the Dreamer dataset has 3 outliers specifically at trial 4, 5, and 20. Next, mutual information has been studied. The conditional entropy quantifies the amount of information needed to describe the outcome of a random variable given the value of another random variable is known. The information entropy, often just entropy, is a basic quantity in information theory associated to any random variable, which can be interpreted as the average level of information. Again, the responses display strong seasonality and normalized amount of information exchange between the corresponding emotional states. We also study cross-correlation. And in the following set of governing equations, Cm is the peaks of the cross correlation sequence, and Rxym is the cross correlation sequence, which is a measure of similarity between two signals measured as a displacement of another. We see how cross correlation sequences has been observed. Here we have the graph of the mean cross correlation on the two chosen datasets. We see that while seed4 session 2 has some irregularity and negative spikes, the dreamer dataset maintains a mostly positive response with 3 outliers. Now we study the Granger causality component. Causality is related to cause and effect. Causal events are those where the cause precedes the effect. Granger causality neither implies nor requires causal interactions. We are trying to determine the likelihood of predicting one event based on what has happened in the past in another event. If we look at the governing equations, and since we will be talking about time series data, they are both autoregressive models. Now, in the context of our problem, we have studied whether one trial, sorry, in the context of our problem, we have studied whether one trial of the sequence is Granger causal to the immediate next or not. The hypothesis is that if a residue or remainder of the previous signal does exist, then the information may increase the likelihood of predicting the next trial. This in turn has given us a set of graph sequences or 25 discrete points for 15 subjects in case of seed 4. We can see very evidently that there exists a striking disparity and not many subjects display any indication that current EEG signals of the trial can be predicted using the immediate previous trial. However, in the case of Dreamer dataset, we see that most of these subjects show an indication towards Granger causality, except a select few. Almost all of the trials have at least one of the subjects displaying Granger causality. This goes further to prove that the sequence of trials are indeed autocorrelated and that each trial sequence can be perfectly predicted with the help of the preceding trial. We study the feature tendency through careful statistical analysis, and we find that by careful feature extraction and selection, we establish that although a residue exists for most uh, consecutive signals, and the measure of that residue as given by observing the PSNR and mutual information, or even the Manhattan distance between the two trials, is nearly constant, it is not enough to indicate replication or causality. Therefore, mean cross correlation and the frequency of Granger causality index, or the number of occurrences for Granger causality for both datasets, were also studied. It is important to remember here that the Granger causality was calculated at 0.05% confidence and at maximum lag of one data point for both datasets. The findings, we find that for seed 4 session 2, the highest number of Granger causal occurrences were at sad to neutral and neutral to neutral emotional state transitions. Although both of these emotional state transitions represent the highest occurrence of Granger causality for seed 4 and also show positive values for mean cross correlation, there was found no satisfactorily high number of occurrences across all the data points. For Dreamer dataset, we find that the highest is at fear to excitement 15 to 16 trial. However, the lowest occurrence of Granger causality is observed by 14 subjects for sad to disgust emotions at trial 9 to 10 pair, and thus yielding lesser possibility of causality between the aforesaid emotional states. Other relatively lower scores of Granger causality are observed for excitement to disgust and excitement to sad emotional states at trial 5 to 6 pair and 16 to 17 pair respectively. So wrapping things up, we find we see that the study has yielded definitive findings such as the information exchange, quality of signals, and causality of corresponding emotional states. We find the analysis of Granger causality particularly useful for determining how likely one time series is in forecasting the other. Finally, we draw that certain transitions of emotional states are more likely to be predictable given its past values than other transition of emotional states. I would like to hereby thank IEEE and NSCC for organizing this conference and the viewers for listening in. My co-author Arpan Sengupta and above all our project guide Dr. Anuradha Saha, without whose guidance this would not have been possible. And now if we have any questions.